Going to do the Unit 5 review here. These are all the equations you should need, and I'll put those on the actual test itself. So let's see what we got here for number 1. 20 kilogram box is pushed at a constant velocity. Somebody put that in bold there. I guess I'm supposed to pay attention to that and think about what that means. If it's going at a constant velocity, that means that the forces are balanced. Okay, across a rough floor, so I guess that means there is friction with a pushing force of 100 newtons. I say I guess and blah, blah, blah. I wrote these questions, so that's what I'm not going to put something in bold if it doesn't for no reason. Okay, so force diagram. I always imagine things going to the right because, I don't know, I guess I'm right-handed or whatever. It's a positive direction. So this is the force of gravity, balancing the normal force, and it's a 20 kilogram box, so I'm going to multiply that by 10 to get the gravitational force, and those are balanced. There's a pushing force of 100 newtons, and it's moving at a constant velocity. Forces are balanced, so that must mean that the friction force is also 100 newtons. That's what the force diagram looks like. What's the coefficient of friction? Well, there's only one equation up here that's got that in it, so force of friction is equal to mu times the normal force. So I think I know everything here except for the mu, right? Force of friction is 100. The normal force is 200. So that's 0.5. Usually we write that as a decimal. If you wrote mu equals 1/2, I'm not going to mark that wrong, but we like decimals better in physics class. Now, if the pushing force is increased to 115 newtons, it doesn't say you have to draw a force diagram here, but if you wanted to just redo it real quick, so you had a force diagram all nice with the details for this. So I'm increasing the pushing force to 115. Friction force is going to stay the same because that doesn't change and the normal force doesn't change. So now the forces are not balanced. Unbalanced force is equal to the force of push minus the force of friction. Of course, unbalanced force is equal to mass times acceleration. And that's going to be 15 divided by 20, so the acceleration is 0.75 meters per second squared. If you're wondering, like, okay, McGrath, like you skipped some algebra there. Can I skip that? Can I skip steps? Sure, but what you can't skip is this and this. Those are two important statements of physics stuff. So I don't care. I don't need to see you doing algebra. That's not very interesting to me. But I do need to see the physics. D, if the box accelerates from rest, as in part C, so in other words with this acceleration, how long does it take for the box to be pushed 2.5 meters? Alright, so now I'm getting into my kinematics equations. So acceleration, initial velocity, final velocity, delta x, and time. So let's see what we know. For it to be pushed 2.5 meters, that's a distance or displacement. So that goes here. From rest means the initial velocity is 0, and I know the acceleration here. So I got 3 things, and I want to find how long does it take. That's my time, so I'm not interested in that. So what equation has those things in it? I think it's this one. So I'm going to write down that equation. This is what you're going to do before you start jamming numbers in. So delta x is equal to 1/2 a t squared, and then the vi is 0, so that term goes away. So looks like I'm going to do some math here, however you want to do this. 2.5, multiply that by 2, it's 5, then divide by that, 5 divided by 0.75, and then I'm going to take the square root of that. About 2.6 seconds. All right. First page done. Number 2. A 5,500 kilogram helicopter accelerates upwards with that acceleration. Draw a qualitative force diagram. So if it's accelerating upward, that's got to be the winning direction. So this force, I'm going to call that force of lift on the helicopter from the air. It's got to be beating gravity. That might be an exaggeration of how much it's winning by, but the thing that the qualitative nature of this, it's got to show that this is bigger. So if this was a test question, for example, that's what I would be looking for to give you the points for this. I'd be looking that you made the lift force bigger than the gravitational force. Write the unbalanced force equation. Unbalanced force is equal to lift is winning minus gravity losing. Use your equation from part B to find the lift force. Okay, so let's see. Unbalanced force is equal to mass times acceleration. Maybe I just write that real quick here before I plug numbers in. So mass acceleration, the lift force, that's what we're trying to solve for, and then the force of gravity here would be 10 times the mass. I think we're good there. I'm just trying to get this pen off my knuckle so I stop smearing all over the place there. All right, so math is happening here on my calculator. It's about 58. I'm going to call that 5,900. You can write down the other digits in that if you want, but about 59,000 rather newtons. All right, here's that one. Suppose a 1,200 kilogram car is traveling at 25 meters per second. Which is about 55 miles an hour. I just put that in there as a reference. You don't need to do anything with that number, just to give you an idea how fast this car is going. Its brakes can apply a force of 5,500 newtons. Assuming there's no forward force while the car is braking, make a quantitative, that means with numbers, force diagram, with numbers, there it is, for the car. Assume that the car is slowing down while traveling to the right. Okay, so my force diagram, I got the force of gravity, which is going to be this times 10. The support force, whatever this car is doing, ain't moving up and down, so that's balancing that. And then if it's moving to the right, just like broom ball, right, the tapping, the braking would be the other way, like this. That's the force of braking. I'll just call that FB, is 5,500 newtons. It's kind of like a friction force, right? It's like the brake pads like squeezing on the discs of the disc brakes. So what's the acceleration of the car? Pay attention to the direction of the acceleration. So the acceleration of the car, this is the only unbalanced force. There's only a loser here, right? Nobody's winning. So I would say unbalanced force is equal to no winners minus this loser, the force of braking there. Now if we want to find the acceleration, unbalanced force is equal to mass times acceleration, and the braking force is 5,500 newtons. So the acceleration is about 4.6. If you did this and didn't get that negative sign, I don't know. I think that right. It doesn't say anywhere that you have to make the positive, that right has to be positive. So I think I would still give you full points for that if you left off the negative sign, but it might get you into trouble for part C here. So what's the stopping distance of the car? Once we start talking about distance, then we're talking about this kind of stuff here. So the stopping distance, let's see, how fast is it going? Initially it's going 25 meters per second. If it's stopping, then its final velocity is 0. And the acceleration, I'm going to put it in as 4.6 here and talk about why you need that negative. And we're looking for the stopping distance. So I'm not interested in time here. And the equation that I need is going to be the Vf squared equals Vi squared plus 2 acceleration, delta x. Okay, so what happens if you don't make this negative? Well, if we just think about what that would mean, it would be like trying to solve for something that's going 25 meters per second, and then it's going to be going 0 meters per second, and it has a positive acceleration. Well, that's impossible, because what does this acceleration mean? It means for every 1 second that goes by, you're going to add 4.6 to this. So if you keep adding 4.6 to 25, you're never going to get to 0, right? So what that means in the equation is you're going to end up trying to take, you're going to get a delta x that's negative, and that doesn't really make sense. In this case, because we're going from 25 to 0, you're actually going to get the right number but the wrong sign. So just be careful with that. If the car is going in the positive direction and it's slowing down, then that must be negative. So anyway, if you do that right, it should look like this. And that makes sense now, because when I move this to this side of the equation, that's going to be negative. Divided by a negative is going to give me a positive delta x. So I don't need to see you doing algebra, and you don't need to see me doing algebra either. So I'm going to push some buttons on my calculator. You make sure that you get the right thing. That's about 68 meters for that stopping distance. All right, looks like a page of Atwood's machines here. An Atwood's machine consists of two masses, 340 and 365 grams. Those are in grams. I need them to be in kilograms. If there's two conversions that you need to be very comfortable with, it's going from grams to kilograms back and forth, and going from centimeters to meters back and forth. One of those is a 3 decimal place shift, and one of them is 2. Of course, centimeters, just like there are cents in a dollar, 100 of them, that's the one that has the 2 decimal place shift. So here, this is 0.34 kilograms, because kilo means 1,000, 1, 2, 3, and this is 0.365 kilograms. So there's my masses in kilograms. Force diagrams for each block. This is the bigger one on this side, so I'm just going to make them kind of next to these here. So if this is the big one, gravity's winning here, and that'd be 3.65 newtons. And the force of tension is losing. And on this one's accelerating up, right? When I let go of them. So the force of tension there is winning. Same string, so those are equal. I'm going to try to make that look smaller. And the force of gravity on this one would be 3.4. newtons, which is that 0.34 times 10. I'm going to go for the total unbalanced force way of doing this. So the unbalanced force total is equal to F, the force of gravity on the big one, minus the force of gravity on the little one, because the tension forces, which are equal to each other, cancel out. So the total unbalanced force total is equal to total mass times acceleration. So that means my 3.65 minus 3.4, that's my total unbalanced force, is equal to total mass, which is 0.705 kilograms, times the acceleration. You could say, I guess you could say total acceleration. That wouldn't really be wrong to say that. But the acceleration is the same for both of these, right? Because they're attached by a string. So let's see, I got 3.65 minus 3.4 divided by 0.705. That gives me an acceleration of about 0.35 meters per second squared. Oh, I guess that was this part. All right. Now this is the half Atwood's machine. I've got lots of practice with this. The hanging mass Einstein practicum was one of these things. There's friction here. Make force diagrams for each block. I'm going to do that next to the blocks. So the force of gravity on this block. This one is 10 kilograms, so the force of gravity would be 100. So the normal force is also 100. And then there's tension force. And then there's friction force, which has to be, if it's actually going to accelerate that way, then that friction force has to be smaller. And I'm being told that that's 25 newtons. So those are not equal to each other. Okay? This block is going to accelerate down, so the force of gravity is winning on that, and the force of gravity on that one is 50. 5 times 10. And then that tension force is losing there. And the tension force is only one string. Those are equal to each other. All right, so I think I got my force diagrams, and I got as much numbers as I could get into it. Find the coefficient of friction between the table and the 10 kilogram block. Well, the coefficient of friction is the mu, and there's only one equation that has that in it. It's this one. So the force of friction is equal to mu times the normal force. So mu is equal to 25 divided by 100, or 0.25. Find the acceleration of the blocks. I'm going to do the same total unbalanced force. So here, what do I have? The tensions cancel out, and then I have this in the winning direction and this in the losing direction. So my unbalanced force total is going to be the force of gravity on the little block, on this one, small m, minus the force of friction. You could say force of friction on the big block, but there is no friction on this, so I think we shouldn't get confused there, right? Now, if I do the math there, that's 50 minus 25 is equal to total unbalanced force is equal to total mass. The total mass is 15 times acceleration. So that's 25 divided by 15. I think that's going to be 1.7, right? And then last part is find the tension force. So where do you go? Which equation, which block do you want to go back to? You could go to either one. For this one, for the small block, you could do the unbalanced force equation. Unbalanced force on that small block is the force of gravity minus the force of tension. So unbalanced force is equal to mass times acceleration. And then the force of gravity on that block is 50 minus the force of tension. So force of tension is going to be, doing some algebra, 50 minus 5 times 1.7. That's about 41.5, it's telling me. Now, if you do it for the other one, we rounded this, you'll get something slightly different, but it should be very close to that. So you could also do it with this block. That would be your other option. I'll let you try that if you want. And last, you knew there was going to be some ramp problem, right? It's going to show up on the test somewhere. A block is placed on a frictionless ramp angled at 35 degrees. Just like my objects like to travel to the right, my ramps like to go down like this. If nobody tells me otherwise, if there's no picture, my ramps like to go down from left to right. But it doesn't matter. Could go the other way if you want. Alright, so I'm supposed to make a quantitative with numbers force diagram. So there's my force of gravity. It's going to be 20 newtons. Now everything else in this force diagram is going to be lined up with this axis system. I'm going to make my perpendicular, my y-axis, and then the first thing I'm going to do is go ahead and break this up, just like I'm plotting a point, over x, straight down y, and my 35 degrees to be down here. Make sure my calculator's in degree mode. It is. And then I'm going to do 20, do this on screen for you. 20 sine 35 and 20 cosine 35. Alright, so I got 11.5 and 16.4, and you should be able, if you got a good diagram and you made your angle not like 45 degrees, then you should be able to tell which one is shorter and which one's longer. And of course you can just do like, oh, sine is opposite, so I know it's that one. So that's anyway, that's going to be the 11.5 newtons there, and this is going to be the 16.4 newtons here. Okay, now this ramp, as of right now in this problem, this is frictionless, so there's no friction there, but I do have a normal force, and this block's not moving up, down in this direction, so that and that have to be equal. Alright, and that's all we can do right now. That's all we got. Find the acceleration of the block down the ramp. So unbalanced force here is just equal to this down the ramp part of gravity. So that was the sine component of that. Unbalanced force equals mass times acceleration. And this is 11.5. So the acceleration is, what is that, 5.8 about? Oops, not newtons. Sorry about that. All right. Now, given the same block and ramp, but now with a coefficient of friction of 0.23, draw a new quantitative force diagram, including the force of friction on the block. All right. That's annoying. Got to draw it again. Who would ask you to do that? So there's that, and then none of this changes, right? This is still 20 newtons of gravitational force. This is still 16.4 newtons. This is still 11.5 newtons. This normal force is still 16.4 newtons, balancing that. But now I've got a coefficient of friction. Anytime you see that, whether you're looking for it or it's given to you, you know you're going to be using this equation, right? So the force of friction is equal to mu times the normal force is 16.4. So 0.23 times 16.4 is about 3.8. And that's pretty small compared to this. I'll try to make it look at least a little bit smaller than that. The force of friction is equal to 3.8 newtons. All right. Now, new unbalanced force equation. Looks like this one, but now I got friction in the losing direction. That's my unbalanced force equation. And then last, unbalanced force is equal to mass times acceleration. This is 11.5. The force of friction we just found is 3.8. And a little bit of math left to do, and then we are done. And shouldn't be surprising that this was the acceleration with no friction, and this is the acceleration with friction. Should definitely be less there. All right.